Hi, hi everyone. Welcome to the last class of TOC. Okay, now let's look at. So this is the QR code of my compiler design textbook. This will be helpful for BTech, MTech, and GATE. And this is the Telegram channel where you can join and do discussions. Okay, so coming to TOC sets. So yesterday we are discussing about Turing machines. Today also our discussion is about Turing machines. Okay. So coming to TOC sets, let us see countability. Coming to TOC sets, let us see countability. Right. So let us say sigma equal to a comma b. Let us say sigma equal to a comma b. Then for sigma star, we can give proper ordering. Proper ordering is a enumeration procedure. Proper ordering, right? Which means I can give 0 length string, 1 length string, 2 length string, so on, right? Therefore, sigma star is a proper ordering, right? Sigma star has a proper ordering. Therefore, you can say sigma star is countably infinite. You can say that sigma star is countably infinite, and every language is a subset of sigma star. Therefore, every language is countably infinite. Every language is countably infinite, right? Every language is countably infinite, right? Now, coming to TOC, you have countably infinite and uncountably infinite, right? Now, countably infinite are sigma star, set of all regular languages, set of all context-free languages, set of all context-sensitive languages, set of all recursive languages, set of all recursively enumerable languages, right? And uncountable are 2 power sigma star, 2 power sigma star, and L not recursively enumerable. L not recursively enumerable. These are all uncountable sets. Okay, 2 power sigma star and not recursively enumerable. These are all uncountable sets, right? Now, how can we prove that these are all countably infinite? How can we prove that? Hi, Mohit. Hi, maths education. Good evening. Good evening. Okay. So, these are all countably infinite. How can we prove that they are all countably infinite? We can do one thing. We can do set of all. We can take set of all Turing machines. Okay. Now, if we encode a Turing machine, it will be a string of zeros and ones, right? Now, if I take set of all Turing machines, let us say Turing machine 1, Turing machine 2, Turing machine 3, so on. Set of all Turing machines, if we take set of all Turing machines, Turing machine 1, Turing machine 2, Turing machine 3, so on. Now this is nothing but strings of zeros and ones. This is nothing but strings of zeros and ones, right? Now this is a subset of sigma star, where sigma equal to 0 comma 1. This is a subset of sigma star where sigma is a 0, 1. Now we know that sigma star is countable infinite. Therefore, set of all Turing machines are countable infinite, and so recursively enumerable languages are countable infinite, and so all the languages which are subset of recursively enumerable are countably infinite. Right? 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 Now we'll see reduction theorem. Now we will see reduction theorem. Now we will see reduction theorem, right? L1 is reducible to L2. This symbol means L1 is reducible to L2, right? So it means that every string in L1 can be reduced to a string in L2 in polynomial time, right? Then what are the various properties that holds on L1 and L2? L1 is reducible to L2, right? Now coming to undecidability, it goes forward. Remember these formulas. Coming to undecidability, it goes forward, which means if L1 is undecidable, L2 is undecidable. And coming to decidability, it goes backward. And if L1 is decidable, about L2, no comment. Right? If L2 is undecidable, about L1, no comment. Right? Now, if L2 is recursive, L1 is recursive. If L2 is not recursive, then L1 is not recursive. If L2 is not SD, semi-decidable, then L2 is not SD. It goes backwards. And if L1 is not RE, then L2 is not RE. Right? Remember all these formulas. They can be helpful in GATE. Okay? They can be helpful in GATE. Right? Now there are few problems that are undecidable. In Turing machines. Okay? 6 undecidable problems in Turing machine. Already we have given decidability table, right? Apart from this, these 6 problems are undecidable in Turing machines. Okay, these 6 problems are undecidable in Turing machines, right? These 6 problems are undecidable in Turing machines. One is halting problem. Halting problem is undecidable in Turing machines. And blank state entry problem and state entry problem and post correspondence problem post correspondence problem and modified post correspondence problem and RE membership, right? So out of these, some problems are easy. Now we know that we cannot say whether a Turing machine can halt or not. Therefore, halting problem is undecidable. Blank state entry problem means given a blank tape to a Turing machine, whether it will enter the final state or not. This is undecidable. And state entry problem means given a string, whether it will enter a particular state is undecidable. Now post correspondence problem means given two sets of strings, let us say this is V, this is U, right? Given two sets of strings, is any combination of V is equal to any combination of U is post correspondence, which is undecidable. And modified post correspondence problem means given two sets V and U, given two sets V and U, we'll start with V1 and U1 and we have to find the combination such that both are equal, right? And recursively enumerable membership. So membership algorithm for recursively enumerable language is undecidable, right? So with this, we have completed TOC, right? With this, we have completed TOC, right? So Rice's algorithm means Rice's theorem, right? So there is Rice's theorem. Rice's theorem says that this is only for RE, recursively enumerable. Rice's theorem is only for recursively enumerable languages. So this theorem says that every non-trivial question on recursively enumerable language, every non-trivial question on recursively enumerable language is undecidable. Every non-trivial question on recursively enumerable language is undecidable. Every non-trivial question on recursively enumerable language is undecidable, right? So what is a non-trivial question? A non-trivial question means sometimes the answer will be yes, sometimes the answer will be no. That is the meaning of non-trivial question. Sometimes the answer will be yes, sometimes the answer will be no. This is the meaning of non-trivial question, right? What is a trivial question? If the answer is always yes or if the answer is always no, that is a trivial question, right? So every non-trivial question on recursively enumerable language is undecidable. Okay, fine. So with this, we will end the TOC. Okay, thank you all. Good night. Jai Hind.